You open your hand. You hold a rock. You feel its weight, its coolness, its solidity. You think, this has mass because it's made of stuff. Atoms, molecules, matter, tiny solid things packed together. And those things have mass because they're made of even smaller solid things. Quarks, maybe, electrons, little billiard balls of reality stacked all the way down. That's the picture. That's what mass feels like it should be. Einstein called this picture a fairy tale, not because atoms aren't real, not because particles don't exist, but because the story you tell yourself that mass is a substance, that it's the amount of stuff in an object is a conceptual trap. A habit of thinking left over from a world that made sense before we looked too closely. Here's the problem. Take that rock. Imagine you could pull it apart, atom by atom, and weigh each piece. Then pull the atoms apart, nucleus, electrons, and weigh those. Then pull the nucleus apart, protons, neutrons. Keep going. Quarks. You expect the mass to add up. You expect that if you sum the mass of every tiny piece, you get the mass of the rock. You don't. The mass of the pieces, measured separately, is less than the mass of the whole. Sometimes much less. A proton weighs about 938 MeV in energy equivalent mass. The 3 quarks inside it, about 9 MeV total. Combined, the quarks account for less than 1% of the proton's mass. So where's the other 99%? It's not in anything. It's not hidden in some smaller particle. It doesn't exist as a substance at all. The mass is in the relationship, in the forces, in the energy of the system holding itself together. Mass, Einstein realized, is not a noun. It's not a thing you possess. It's a measure of something else entirely, something about structure, confinement, and energy locked in configurations that resist change. You think you're holding matter. You're holding a pattern. A standing wave of energy, a knot in a field. And the moment you stop thinking of mass as stuff, the moment you stop searching for the tiny solid thing at the bottom, everything Einstein said starts to make sense. Push a shopping cart. It resists. Push a car. It resists more. You call that resistance inertia. And you think inertia is a property. The object has some internal stubbornness, some quality of the matter itself that fights back when you try to accelerate it. Newton told you that. He said inertia is proportional to mass. The more mass, the more resistance. Clean, simple, obvious. But he never told you why. Why does mass resist acceleration? What is it about a kilogram of steel that makes it harder to push than a kilogram of foam? They have the same mass. They should resist the same way. And they do. But why? Newton didn't know. He admitted he didn't know. He called it an inherent property and moved on. Einstein didn't move on. He asked, what if inertia isn't something the object has? What if it's something the object does in relation to everything else? Here's the crack in your intuition. You think of an object as isolated. You push it, it resists. The resistance feels local, like it's coming from inside the object, from its mass. But Einstein's general relativity suggests something disturbing. An object's resistance to acceleration is tied to the structure of spacetime around it. Inertia isn't a property stored in the object. It's a manifestation of how the object is embedded in the geometry of the universe. This is called Mach's principle, and Einstein flirted with it his entire life. The idea is this: your mass, your inertia, is determined by the gravitational relationship between you and every other massive object in the universe, the distant stars, the galaxies, the cosmic web. You think you resist acceleration because of something inside you, but maybe you resist because the universe resists, because spacetime itself has structure. Because when you try to accelerate, you're not fighting your own matter, you're fighting the curvature, the frame, the gravitational topology of everything around you. This isn't proven. It's not settled. Einstein himself went back and forth. But here's what is settled. Inertial mass and gravitational mass are exactly the same. Not approximately, not coincidentally. Exactly. The mass that resists your push is identical to the mass that responds to gravity. Newton thought that was a strange coincidence. Einstein thought it was a clue. And the clue pointed to this: mass is not a little ball of resistance sitting inside an object. Mass is a relationship, a way that energy couples to the geometry of spacetime. You don't have inertia. You are a curvature in the field. And when you accelerate, the field has to bend. That bending, that geometric resistance, is what you feel. Inertia isn't in you. It's between you and the universe. You've seen the equation. Everyone has. Equals mc squared. You were told it means mass can be converted into energy, that they're interchangeable. That if you take a chunk of matter and do something clever, split an atom, fuse a nucleus, you can turn the mass into energy. Liberate it. Release it. That's how it's taught. That's how it sounds. And it's backwards. Einstein didn't say mass converts into energy. He said mass is energy, not a source of it. Not a container for it. Not something that becomes energy under the right conditions. Mass is energy that's already there, just in a form that isn't moving. Energy that's trapped, localized, bound into a configuration that looks, to you, like a persistent thing. Here's the shift. You think of a particle, a proton, an electron. A rock as an object that has energy, kinetic energy if it's moving, potential energy if it's in a field, and rest mass, which is something else, a separate category. Einstein said no. Rest mass is energy, the rest energy. The energy of the system when it's sitting still in your frame of reference. It's not a different kind of thing, it's the same thing, just not expressed as motion. The equation doesn't describe conversion, it describes equivalence. When you convert mass into energy, say, in a nuclear reaction, you're not transforming one substance into another. You're releasing energy that was already there. You're breaking the bonds, the structure, the configuration that held the energy in place. The energy was always energy. It was just confined. And here's the part that breaks the intuition completely. Energy has mass. Not metaphorically. Literally. Heat has mass. Light has mass. The kinetic energy of a moving object adds to its mass. If you heat a kettle, it gets heavier. Not because you added particles, because you added energy, and energy gravitates. Energy resists acceleration. Energy is mass. A box of bouncing photons, massless particles. Each one individually has mass as a system, because the energy is trapped, confined, moving, but not escaping. This is what Einstein saw. Mass is not a substance that can turn into energy. Mass is what we call energy when it's not going anywhere, when it's locked into a pattern, a standing wave, a bound state. You think of matter and energy as two different things. They're not. Matter is frozen energy. Mass is the label we give to energy that stays in one place long enough for you to point at it and call it an object. Equals MC doesn't describe a transformation. It describes an identity. You are not made of matter that contains energy. You are made of energy that looks like matter. You weigh yourself 70 kilograms, 80, 90, whatever the number is. You think of it as the sum of your parts, cells, molecules, atoms, electrons and protons and neutrons, stacked and bound and held together. You assume that if you could weigh each particle individually and add them all up, you'd get your mass. You wouldn't even be close, because most of your mass, about 99% of it, doesn't come from particles at all. It comes from nothing. Not poetically, not metaphorically, literally nothing. Empty space, the seething, roiling quantum vacuum inside every proton and neutron in your body. Here's how it works. A proton is made of 3 quarks. 2 up quarks, 1 down quark. You can measure their masses. The up quark, about 2.3 MeV. The down quark, about 4.8 MeV. Add them up, and you get roughly 9 MeV total. The proton itself weighs 938 MeV. You're missing 929 MeV. That's 99% of the proton's mass. So where is it? It's in the gluons, the force carriers. The quantum field fluctuations that bind the quarks together. These gluons are massless individually. They weigh nothing, but they move, they fluctuate, they interact with themselves and with the quarks in a furious, confined dance. And that motion, that energy of confinement, has mass, not because the gluons suddenly become massive, but because the energy of the system, trapped inside the proton, contributes to the proton's inertia, its resistance to acceleration, its gravitational effect. Mass emerging from motion, from interaction, from the structure of the forces holding the system together. You are not made of particles. You are made of fields, of interactions, of energy densities bound into temporary stability. Here's the deeper problem. Quarks themselves aren't little solid things. They're excitations in a quantum field, ripples, disturbances. You can't pull one out and hold it. If you try to separate a quark from a proton, if you pump in enough energy to break the bomb, the energy you add doesn't free the quark. It creates new quarks. The field responds to your interference by spawning more particles. This is called confinement. Quarks don't. exist as isolated objects. They only exist as parts of bound systems. And the mass of those systems comes almost entirely from the binding from the energy it takes to hold the configuration together. Your body is about 710 atoms. Most of your mass is in the nuclei of those atoms, protons and neutrons. And most of the mass in those protons and neutrons is not in their constituent particles. It's in the fury of the quantum fields between them, the forces, the fluctuations, the gluons looping and splitting, and recombining in a space smaller than 10 meters. You think you're made of stuff. You're made of confinement, of energy that can't escape, of patterns held together by forces that resist dissolution. Mass is not what you contain. Mass is what it costs to hold you together. Drop a ball, it falls. You think gravity pulled it. The Earth's mass attracted the ball's mass. To objects, to masses, pulling on each other across space. Newton's law, simple, intuitive. Einstein said that's not what's happening. Not even close. There is no pull. There is no force reaching across space, grabbing the ball, yanking it downward. Gravity is not a force acting on mass. Gravity is mass. Or rather, gravity is what mass does to the stage on which everything moves. Here's the picture you need to abandon. You think of space as a static backdrop, an empty container. Objects sit in space, and forces act between them across the emptiness. Mass here, mass there, invisible force lines stretching between them. Einstein said space isn't a backdrop. Space is a participant. Space has shape, structure, curvature, and mass doesn't pull on other mass. Mass bends space itself. It warps the geometry, and objects moving through that warped geometry don't feel a force. They feel nothing. They simply follow the straightest possible path through the curved space, a geodesic. When you drop a ball, the ball isn't being pulled. It's moving in a straight line, the straightest line it can, through a spacetime that's been curved by the Earth. You think the ball accelerates toward the ground. The ball thinks it's floating freely, unaccelerated, while the ground accelerates, up to meet it. This is the equivalence principle. Einstein's deepest insight, the one he called the happiest thought of my life. If you're in free fall, if you're dropped, if you're in orbit, you feel no gravity, you feel weightless. Not because gravity turned off, but because you're moving along a geodesic. You're doing what spacetime tells you to do. No force is acting on you. The only time you feel weight, the only time you feel gravity is when something stops you from following that geodesic. When the ground pushes up, when a chair resists. That resistance, that deviation from free fall, is what you experience as weight. Gravity isn't a force pulling you down. It's the absence of force. And weight is what happens when something interrupts that absence. Now here's the turn. Mass doesn't just curve space. Mass curves spacetime, space and time together, the geometry of reality itself. A massive object doesn't just tell other objects where to go. It tells them when to go. It slows time near its surface. Clocks tick slower nearer than they do in orbit, not because the clocks are broken, because time itself is stretched, warped, dragged by the presence of mass energy. And that curvature, spatial and temporal, is what you call gravity. Mass doesn't have a gravitational field. Mass is a curvature in the field of spacetime. When you stand on the ground, you're not feeling the Earth's mass pulling you. You're feeling the Earth's curvature pushing space itself upward beneath you, and the ground blocking your path through that curved geometry. You think gravity acts on mass. Gravity is mass expressed as geometry. You don't fall because you're attracted. You fall because spacetime is curved, and you're following the only path the universe gives you. You've heard the story. Particles move through the Higgs field. The field resists them. That resistance is mass. The Higgs boson was discovered. The mystery was solved. We know where mass comes from now. That's the story. That's what everyone says. And it explains almost none of your mass. The Higgs field is real. The Higgs mechanism is real. In 2012, CERN found the particle. Peter Higgs won the Nobel Prize. None of that is in question. But here's what gets left out. The Higgs field gives mass to fundamental particles, electrons, quarks, W and Z bosons, particles that, without the Higgs, would be massless. They'd move at the speed of light, like photons. The Higgs field breaks the symmetry, interacts with these particles, and gives them rest mass. That's important, that's profound. But you are not made of fundamental particles wandering through the Higgs field. You are made of bound systems, atoms, nuclei, protons, and neutrons. And as you just learned, 99% of the mass in a proton doesn't come from the quarks. It comes from the gluon field, the quantum chromodynamic energy, the confinement. The Higgs mechanism gives the quarks their tiny rest masses, those 9 MeV out of 938, the other 99%. The Higgs has nothing to do with it. That mass comes from the strong force, from the energy of the gauge fields, from the fact that quarks are confined and the energy of confinement gravitates. So when you step on a scale, and it says 70 kilograms, only about 1% of that, less than a kilogram, comes from the Higgs mechanism. The rest comes from forces, from binding energy, from the quantum seething inside every nucleus in your body. You were told the Higgs field is why things have mass. It's why some things have some mass. It's a piece of the story, a crucial one, especially for particle physics and symmetry breaking. But it's not your story. Here's the deeper irony. The Higgs field was introduced to solve a specific problem. Why do W and Z bosons, the carriers of the weak nuclear force, have mass, while photons don't? The math of quantum field theory said they should all be massless. The universe disagreed. The Higgs mechanism resolved the contradiction. It allowed particles to acquire mass without breaking the underlying symmetry of the equations. Elegant, beautiful, revolutionary. But it doesn't explain the mass of composite objects. It doesn't explain why a proton weighs what it weighs. It doesn't explain you. You are not a particle in a field. You are a bound state of quantum fields, held together by forces that themselves carry energy, and that energy trapped, confined, oscillating manifests as mass. The Higgs gives mass to the fundamental. The strong force gives mass to the composite. And most of what you are is composite. You exist because forces won't let you fall apart. And the cost of that resistance, the energy price of your coherence, is what you call your mass. The Higgs field is not the origin of mass. It's one mechanism among several, a footnote in your existence. You are not held together by the Higgs. You are held together by confinement, by gluons, by the refusal of the quantum fields to let you dissolve. You still want there to be a thing, some particle, some field, some substance at the bottom of it all that is mass. A final answer. A place where the chain of explanation ends and you can point and say, there. That's what mass is made of. There isn't one. Mass is not made of anything. It's not a substance. It's not a property that objects possess independently. Mass is a pattern, a relationship, a label we give to certain configurations of energy and spacetime that persist long enough to look like objects. Here's what Einstein saw. He saw that energy and mass are equivalent, that inertia and gravity are two aspects of the same phenomenon, that spacetime is not a stage but an actor, that the geometry of reality responds to the presence of energy, and that response, curvature, resistance, confinement is what we call mass. Mass is not fundamental. Energy is fundamental. Fields are fundamental. Spacetime is fundamental. Mass is what emerges when those things interact. Think about a proton again. 3 quarks, a cloud of gluons. The quarks have a little mass from the Higgs. The gluons have none. But the system as a whole, confined, bound, stable, has mass, not because mass is stored inside it, because the configuration itself, the pattern of energy trapped in a small region of space, resists acceleration and curves. Spacetime. The mass is in the structure, in the relationships, in the fact that the energy can't escape. Now think about a photon. Massless. It moves at the speed of light. It doesn't curve spacetime on its own, not significantly, but trapped to photons in a perfectly reflective box, bouncing back and forth. They're still massless individually. But the box, the system, has mass, because the energy is confined, because from the outside, the system resists acceleration. It gravitates. It behaves like it has mass. The photons didn't change. The confinement created the mass. Mass is a consequence of boundaries, of limits, of energy that can't leave. Here's the final turn. You think of yourself as a solid, coherent object, a thing with a definite mass, a person. But you're not solid. You're mostly empty space. The nucleus of an atom is 100,000 times smaller than the atom itself. If you removed all the empty space from your body, you'd fit into a grain of sand. Less. And even the parts that seem solid, the protons, the neutrons, are not solid. They're quantum fields. Probability clouds, excitations, disturbances in the electron field, the quark field, the gluon field. You are not a collection of particles. You are a standing wave, a stable configuration of fields that has existed long enough for you to call it you. And your mass, you're 70 kilograms. Your inertia, your weight is not a measure of how much stuff you contain. It's a measure of how much energy it takes to hold that pattern together, how much the configuration resists being torn apart, how much spacetime curves in response to your existence. Mass is not what you have. Mass is what you cost. Einstein didn't discover what mass is made of. He discovered that mass isn't made of anything. It's a shadow, a symptom, a consequence of deeper structures, fields, geometry, confinement, energy that we can describe, predict, measure, but never hold in our hands. You wanted mass to be a thing. It's a story, a useful fiction, a word we use to describe the way energy shapes spacetime and spacetime shapes motion. You are not made of matter. You are a pattern that matter makes, a knot in the quantum fields, a temporary resistance to entropy. And the universe doesn't care what you call it.